Moron. Excuse my French. Okay, so obviously, again, this is going over the assumptions that we have to make on every inference problem. Number one is going to be a random sample from population of interest. There is one other variation to that, and that would be if we were doing an experiment instead, then it would be random assignment, okay? But most of the time it's going to be a random sample. Number two is we have to show, in order to do that inference, that my sampling distribution is going to be approximately normal. And how do we show approximately normal? And this is where last chapter came into play. Well, there's basically two ways that we're going to do this. But we have to understand, is it a mean? We have two different ways. Is it a proportion? We have one way. So this is a proportion, so we're going to use n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So again, this is where we have to know our rules. I have a proportion. I'm going to use the successes and failures have to be both be greater than 10. Okay, so I have deemed this approximately normal. So again, normality is going to set my sample size on the bottom side as far as a minimum sample size. Independence sets it the other direction. And what's my rule for independence that never changes? As my sample size is less than 10% of my population. Okay. So again, understanding a little bit about the brackets that go along in here. If we're just talking about the bracket around the square root sign, that's my standard error. In other words, the error is also called the standard deviation. So that should look similar to what we pulled out earlier. We pulled this equation out of the formula sheet just a second ago. Okay. The bottom part of this is now we're going to include the product of z with it. And when we do that, what we're doing is we are creating a margin of error. Okay. And that's then understanding what happens with that margin of error. So my margin of error gets smaller when, okay. So again, this is going to, these adjustments are going to make my margin of error get smaller. Okay. So if I make z smaller, that means I'm going to decrease. You can't already tell that's decrease. I'm going to decrease my confidence level. Okay. Because so z gets smaller. So if I came back up here and I don't think I drew a diagram anywhere. Okay. We can draw a diagram out here if we want. There's our curve. If we want to be, let's say 90% confident, there's that. So that means I'm going to have a z-score at 1 point. We'll look at those later. I could be more confident. I'm going to move that out to 95. I could be even more confident and move that out to 99. So when I increase my confidence, this is talking about increasing my confidence. This z-score is equal to 1.64 technically. This is going to be z is equal to 1.96. So we can see that that value gets larger. So if I'm going to narrow that up, that means if the z-score is going to get smaller. Okay. Standard deviation gets smaller and less variability. In the population. And as n gets larger, we talked about this a little bit last chapter. If we're going to decrease it by half, that means it has to be 4 times as big. Okay, again, we're talking about this number here. As this number gets larger, that's going to cause that fraction to technically get smaller. Okay, so that is why we're going to decrease that margin of error. Okay. Anything since p is unknown and n is large, we estimate p with p hat. So that is the principle of what we go behind here. We don't know what my population proportion is, but we're going to assume that since my sample size is large enough or sufficiently large, we're now going to use p hat as an estimate of p. Okay, but that makes us make sure everything is right. All right, so We have some confidence levels to fill out here. We're going to use inverse norm to do that. So if we drew a picture real fast, we don't see this one a whole lot, but it's here anyway. I want to be 80% confident. Okay. If I want to be 80% confident, what critical value am I going to use? That's the start questions we have to start figuring out. Okay. So this, again, this goes back to unit 1B. If I have 80% in the middle, what's left for each tail? There's 20% overall, so that means that we have 10% for each tail. So this again is going to be where you prefer your inverse norm operating at. I'm going to go a left-hand tail, which is 10%. I'm going to have a mean of 0 and a standard deviation of 1, and that's going to give me a critical value then of z is equal to a 1.28. And because we're going to have one on the left and one on the right, it's going to be a plus or minus situation. In the second one, we want to be more confident. So we're going to increase this to be a 90% in the middle, which is exactly what we did for the activity. So if I have 90% in the middle, that leaves me with 10% left over. So now I've decreased my tail in half. Now we're talking about 5% tails. And again, if you know your calculator, you can use the center feature here if you want. However, I won't just show that in my notes. And I guarantee you, we'll do these enough times that you'll just start remembering what they are. And even if you don't remember what they are, I'll show you a quick, simple way to do that when we get into t distributions later on. But we did this one already. We did this one in our activity today, and it is 1.64. So you can see my z-square, critical value of z has gotten larger. Okay, the more confident I want to be, the larger my z is going to be. All right, so we'll draw another curve representing 95%. So now we're going to get even wider yet. I want to be 95% confident. So that means my tail is getting smaller. We're only talking about the upper 2.5% or the lowest 2.5%. So we're getting to really rare stuff here. We're going to inverse norm. 0.025, 0 and a 1. And again, we didn't do this yet, but that's going to be a 1.96. And lastly, we're going to be uber confident we capture that mean, or that proportion, excuse me. We're going to roll it out here at 99%, which leaves me with 1% left over. So there's a 0.5% on this tail and a 0.5% on this tail. And if we convert that 0.5% into a decimal, that's 0.005. And we are rolling out there at 2.58. To make sure all parts of a complete AP answer are answered for a confidence interval question, we're going to have acronyms. So in this, in inference, we're going to have two acronyms that we need to know. Okay, if we come across an interval, we're going to panic. If we come across a hypothesis test, we're going to use phantoms. Okay, and we just have to know what the acronym stands for. And again, after enough practice, you don't actually have to use the acronym. It is just there to help you get all the pieces parts in place that the grader is going to look for when they go through your response. Okay, so P is going to stand for the parameters. What part of the population are we going to be looking for, as well as this is where we write down everything. Okay. A stands for assumptions. With any inference problem, we have to go through and make sure our assumptions are met. So therefore, we know that we are okay conducting inference procedures on this particular sample. N stands for the name of interval. Now, as much as we'd love to do with Bob or Judy or Tom or Joe, those are not names that we're talking about here. Okay, the names that we're talking about here, we could have a one prop Z interval, a one proportion Z interval, or it could be a one sample Z interval for proportions. It can be a lot of things, but we're gonna have a one prop and a two prop, meaning that is a common abbreviation for interval, so we're okay. We can rotate this over to means. We'll do means next chapter. But since we're here talking about them, we'll go ahead and include those as our name list. And in reality, we also have a 1 and 2 sample for a T interval, and I'll just abbreviate those. Again, there's 6 possible names that we'll have there for intervals. In reality, we'll see the Z interval very, very infrequently. I don't know if we'll ever see a Z interval because we have to know the population standard deviation to do that Z interval, and very rarely are we going to know the population standard deviation. So I think it's pointless to go over, but it still shows up in the book. So after we have made sure all of the inferences assumptions are met, and we have named our interval, we are actually going to construct the interval. So I'm going to have that proportion, okay? And then lastly, we are going to have a conclusion in context. So our first example for our first interval, before a project, a student randomly sampled. So again, we'll just get in the habit of when I read through a problem, I am looking for a random sample. It just has to be there. Okay. So in other words, I'm going to do this problem, and there's 2 ways to work at this. I could do the entire problem and then go back through and check off panic and make sure I got all the parts of panic there. Or I could just write down panic and just go through step by step and put those parts into my answer. So it's totally however you want to use it. I'm not going to tell you to use it one way or the other. Okay. We randomly sampled 182 students. So that means that N is going to be 182 students. To determine if the majority of students were in favor of a proposal to build an indoor soccer complex, he found that 75 favored the proposal. So because it came from a sample, I'm going to have a p hat of 75 divided by 182. And therefore, I am going to know that that p hat is going to be 41. Find and interpret. So typically, this is never going to tell you find, but the conclusion part is going to be our interpret anyway. So we're covered. 95% confidence level. So if we're going to use a 95% confident, we're going to use what critical value? Do you remember? 1.96. So again, it's just over time, we'll do these enough that you'll just know that's going to be 1.96. Okay. All right. And in this case, though, it said that P is the true proportion of students who favor the proposal. So it told me what my population parameter was to start with. If it didn't tell me that, then we would have to go through and do that. Okay. All right. So we have taken care of our parameters. Next on the list is our assumptions. What's our first assumption? Random sample of KSU students. What's our second assumption? My sample distribution should be approximately normal. And we have to give evidence of why it is. So why is it approximately normal? And again, we have to go back to, we are doing a proportion. So that means that we're going to have to do n times p. So we're going to have 182 times 0.41. That is greater than or equal to 10. 182 times 0.59 is also greater than or equal to 10. Both of those check out. You could have gone with successes greater than 10. It's because there was 75 successes. And that means that we had, what, 107 failures? Okay, you could have just said that, okay? We don't always have to go to n times p, okay? Not all the time. If we have successes and failures, we can just write it in terms of successes and failures because those are the same two things, okay? What is assumption number 3? My sample size is large enough because of approximately normal. We also have to show that it's small enough that it remained independent. So we have to assume that 182 is less than 10% of all KSU students. And that checks out okay. Okay, assuming there's more than 1,820 students at KSU. All right, so we've taken care of our assumptions. The next thing is, we're gonna have to give it a name. What name are we gonna give it? We're gonna consider this a what? How many proportions do we have? 1, so this is a 1 proportion Z interval is what we're creating. Again, we are estimating the proportion of people that we feel would vote in favor of the indoor soccer stadium, okay? So now it becomes, well, we have to create that interval. So I will, for the first one here, I'll go ahead and write the formula. Writing the formula is completely irrelevant. However, I just have it here on the first one so we can have a go with it. And again, notice that I use p hats in there because we're using sample proportions, okay, versus a population proportion. So p hat was 41. Plus or minus, we decided to use a critical value of 196. My sample proportion was 41. So that means we're going to have a 59 for nays. And we had 182 in my sample size. On this particular problem, I will go ahead and write this. It's 0.0715. So that means if we took 41 and added on my margin of error, we're going to get a right boundary of 0.4815. If I took 41 and subtracted off the 0.0715, that's going to give me a left boundary of 3385. So I have created a margin of error. So this is just like we did on the fish or the sloths, or in our case, the movies, is we created a confidence interval. We are 90, based upon the procedure used, we will have correctly captured the true proportion of KSU students who voted in favor of it with this interval. Okay, so it should be between 33 and 48. We think it's around 41, but we gave ourselves a 7% margin of error, roughly. Okay, so we have created the interval. That's done. So my last step is to write a conclusion. And this is also the interpret part. We are, and again, this goes back to those Mad Lib statements we just have to start getting. We are 90% confident, except we are not 90% confident. We are 95% confident. The true, and again, this is where you just have to pay attention to the detail on what we're doing, okay? I can't tell you how many times I'll grade a paper and somebody will write down the true mean, because later on we start doing with proportions and means all at the same time. They start mixing together. and you'll write down you've done a proportion problem, but then you write down the true mean. Well, you've nixed you've sunk yourself. So make sure we're paying attention to what we're doing. The true proportion of KSU students being in favor of a new indoor soccer complex lies between 33 and again, converting to a decimal is irrelevant there. I just like to do it for proportions. I usually like to turn it into a percent. But you could have written 0.338524.815. And again, like it has been all year, there is no set rule for rounding. You could go with 2 decimal places. You could go with 1. You could go with no decimal places. It's going to be a range of answers that the grader is going to look for. Oh, this is a long day, isn't it? Okay. Well, we still have one more example and one more concept to talk about. All right, here we go. The Gallup Youth Survey asked a random sample of 439. Okay, so again, as we walk through this, it's a random sample again. We just know that I'm going to have to need that. So I'll go ahead and highlight that. So it's I've made myself aware of it. We have 439 US teens. So I'm going to guess my sample size is going to be 439 US teens, age 13 to 17, where they thought teachers positively influenced their life. Of that, 246 said yes. So that means that my p hat is going to be 246 out of 439. Which is going to be, if my dry fingers would allow my page to turn, 0.56. Construct and interpret a 90% confidence interval. So if we're dealing with 90%, we're going to use what for a critical value? 1.64 is my critical value. Okay. Okay. And I'm supposed to make sure, again, my P is coming from a population where P hat comes from a sample. So we have to indicate, again, the proportion of all 13 to 17-year-olds answering yes. Oh, we have bells back now. Okay. Okay. Again, we'll just go through it. I have done the, I don't know, can we even see it? We can. All right, we've taken care of our parameters. Assumptions. My number one assumption, as always, random sample of teens. Number two thing we look for, and we do that because, not do that because, we're going to do it how? And again, you could do it successes and failures. I was actually going to do that this one. I just totally blew by it. But it's okay. So my sample size is sufficiently large. I have trouble with that word. 3. Independent. We'll assume that 439 is less than 10% of all 13 to 17-year-olds. Okay, all 3 assumptions are taken care of. Next, it has a name. What name are we going to give this one? A 1 prop Z interval. So, what is my interval going to be? My point estimate starts in the middle. My critical value is 1.64. My p-hat value is 0.56. Its complement is 4.4, divided by my sample size, which is 439. And again, this one I'll just jump straight to the interval 5211 and 5989. Okay, we have named it. We have found the interval, and now we need to conclude. What are we going to conclude? We are 90% confident. The true proportion of all teens between 5211 and 5989. Okay, one last concept of our sample size, and then we can end our misery for the day. Again, this is a start question, so we're going to see this. Again, we're talking about, notice that this is just the margin of error. So we've pulled out the margin of error part of the equation. So really the only thing missing is the point estimate. Okay. And what we have to is when we're doing a sample size problem, we're always going to round up. So if it comes up to be 32.1, we're going to round that up to 33. Okay. No matter what, we always round up. Okay. P hat is guessed value. If note P hat is a guessed value. If no previous estimate is given, then we'll use something like P hat, 0.5 as my estimate. And we'll show you why here that matters in the end. Okay. So a media analyst would like to find a 95% confidence interval estimate within 0.03 for the proportion of all households to watch Netflix regularly. How large a sample is needed if the prior estimate for P was 0.15? Okay, so once again, we're doing our margin of error formula, which is written above. So I'm not going to, I'll write it out again. Not that it matters. It's written above, but we'll write it in there. Okay, do we know what our margin of error is? Yes, it wants the margin of error to be 0.03. P, again, that previous estimate was 15. So that means that 85% of people don't watch Netflix. I'm guessing that proportion has changed dramatically in the last year. My sample size, well, that is actually what I'm trying to find. So that's going to be unknown. So now your algebra skills have to take over, except I screwed this up. What have I screwed up? I have forgotten z, so there should have been a z in my original equation. I also don't have room for my z, so we'll erase the equal sign and we'll get z tucked in here. What is going to be my critical value? We're going to be 95% confident, so that means we're going to use the 1.96. Now your algebra skills got to take over. Okay, we're going to divide that 196 over. We're going to square both sides to get rid of the square root. We're going to trade places from numerator to denominator with n and that other quotient squared. And hopefully, if you do all your algebra right, you're going to get n as I shouldn't say algebra, your order of operations correctly. We're going to get 544.2, which means that 545 people should be asked. Okay. Example 4. The media analyst executive would like to find a 95% confidence interval to estimate within 0.03 the proportion of all households that watch Netflix regularly. How large a sample is needed if we have no reasonable prior estimate for P. So this is actually the same exact problem. The only difference is we still want 0.03 for my margin of error. I want 1.96 as my critical value, but I was given no reasonable prior estimate. So that means we're going to go with 0.5 and 0.5. So the only thing different about this problem is we change my value of P. And we're going to see what is the impact then on the sample size needed. And if we do the algebra, this turns out to be 1067.1. So that means that we need 1068 people. Okay, so again, we can see we almost 1090. So we almost doubled what sample size needed. Okay, because we didn't know what my original proportion was. We went from a 15% rate to a half 50% rate. Okay. Alrighty, I'm going to shut this off because we have hit the end of that.